but then I need the actual mass, which is what we're solving for number 1, to get to there.
Oh, makes sense because like you're doing 12.4.
Yeah. Oh, okay. Wait, what is the big? What is the big?
All right. What kind of approach do we need for this problem? So this is one of our throwback problems, right? This is back to earlier material. So I'm asking you to kind of recall things earlier in the class. So the first thing you have to do whenever you encounter a problem like this is figure out like what set of tools do I have that I can apply to this problem, right? So what are some tools that we have that might address this one? What's the big set of tools? Isabel?
You have a set of, what I do is I start with P first, and you have a set of ratios.
Oh, okay, so Isabel started with the second part. Let's practice like naming the problem type, so that calls up like a set of techniques that we could use. So what kind of problem type is the second part? What do we call that when we're given percentages? Amarachi? Yeah, it's the method we use to find empirical formula. That's fine. That's a perfectly good approach, and yeah, that's an empirical formula problem. We need information from both parts. So in order to answer the question. So in the first part, what kind of question is that, Dan?
It's an ideal gas law question.
Yeah, it's an ideal gas law question in disguise, right? I mean, it's a little bit disguised. So why do I say it's kind of in disguise? What are you used to being given? Well, what's the ideal gas law? EV equals nRT. We're used to being given those things, right? And what we have is we have a mass, and we're asked about molecular weight, right? That doesn't directly appear in there, right? Okay, so where does like mass and molecular weight maybe come into play here? What do we use molecular weight for sometimes? Maybe when we're given a mass. To find moles. Oh, maybe that's the trick. So if we have a mass of something, what do we need to do to that mass to figure out the number of moles of it? We divide by, I give you 1 gram of something, I want to know how many moles that is. You divide by the molecular weight, right? So this N equals the mass divided by the molecular weight. Is everyone comfortable with that? So with that, we can rewrite this, right? We could write mass over molecular weight equal, times RT equals PV. What are we really trying to solve for here? What are we trying to solve for? What is the molar mass, right? So we're after the molecular weight here, right? Is everyone comfortable with that? So we've taken the ideal gas law and we've just made this one substitution, and now maybe we should solve for molecular weight. Is everyone comfortable with that? So let's just solve for that thing that we want. So molecular weight's going to equal what? Let's see, mass over or mass times RT divided by PV. Does everyone see that? I'm just doing algebra, right? Everyone comfortable with this? Does everyone see how we got to there? So do we have all of these things? Do we have all of these things? Well, what's the mass? 4.24 grams. Okay, what's R? 0.0. Do you have to know R? It would always be given to you. 821 liters, atmospheres per mole Kelvin. That is a constant. How about P? P is, in the problem it says 1.05 atmospheres. Right? How about T? 298.15. Well, that's not what it gives in the question. Why don't we just use what's given in the question? Yeah, because this unit right here is Kelvin, and we need to make sure that all the units are the same in the question. So we've got mass, R. What are we lacking here? Volume. What's the volume? Yeah, 1 liter. 1 liter is what gives us that mass. right? So we've got 1.00 liters there. How many unknowns do we have? We only have one left, right? That means we can solve this equation, right? All we do is plug in those numbers. Everyone comfortable with this? Did anyone get a number? Go ahead, Dan.
98.74.
98.74. When you plug those in, 98.74. And what's the unit, Dan? Yeah, grams per mole. Okay? Is everyone comfortable with how we approach that problem? Okay, we sort of set it up. We didn't have exactly the information we needed, but we knew how to get there using sort of our conversion to moles. Okay, so now we have that. Now, Isabel, now it's time for you to shine. What are we going to do with this part B thing? What do we do when we're solving an empirical formula problem? The first one was an ideal gas problem. The second one was an empirical formula problem. What's the first step?
Basically what I did was keep all of the
Yeah, so let me just articulate what you did. What you did was you said, I know I have 100% total. Let's assume I have a 100-gram sample, right? Because what I'm after is the ratio of elements, so I don't care what size sample. I could say a 1 kilogram sample and use those percentages to calculate how many grams each, right? But it's easy just to say, I have a 100-gram sample. In a 100-gram sample, how many grams of carbon would there be? 12.1 grams of carbon in that sample. How many grams of oxygen? 16.2 grams of oxygen. And how many grams of chlorine? 71.7 grams of oxygen. And I need to get out of those grams what? Where do I want to get to? I need a mole ratio, right? So whenever I have a mass, how do I get to moles? I divide by the molecular weight, right? So here we're talking about atomic weight, so the atomic weight of carbon is, so this is about 1. So this is about 16, right? Oxygen molecular weight is about 16. So this is grams per mole each time, grams per mole each time. So the unit here would be mole. There's 1 mole of that. How many moles of oxygen? 1 mole of that. Remember, we're interested in like whole number ratios, so we don't really care about the decimals here. And chlorine, it's like 35 point and change, right? So this is going to be 2 moles. So now I know the empirical formula. It would be COCl2. Everyone comfortable with this? So now, how do we see if that is the actual formula, like the molecular formula, or the empirical formula? What do we do next? Erica, you want to go?
No, I just want to say that I didn't do the first thing. I just calculated that, and from that I got the molecular mass, and I got the same thing. Like without doing the ideal gas.
Yeah, I know, but without the ideal gas law, we can't know whether this is an empirical formula or a molecular formula. And so you actually just answered the question. She found the empirical formula and got the molecular weight of this, and it turned out to be 98.7. So the fact that those two correspond means this is the molecular formula. You actually need both parts. You need something to tell you whether that's the actual mass of the thing. You know, another alternative was that number could have been twice as much, and so you would have had to double, right? Everyone know what I'm talking about? So both parts together allow us to know that this is both the empirical and the molecular formula. Is everyone comfortable with this? Okay. So anyway, people have asked and told me that they really enjoy getting these throwback questions, so I think this is a good one. This is a fun one. Let's see. Announcements. Thursday, we have another, what promises to be wonderful seminar. Professor Janet McDonald. She's going to talk about inorganic nanoscale natural and unnatural product synthesis. Sounds fascinating. I'm not familiar with her work, but it sounds incredible. So that will be right here at Common Hour. And after her talk, you are welcome to have lunch with the speaker. I don't know if any of you did that with the last speaker, who was also wonderful last week. Go have pizza with these people. They're here to interact with you. So make your lunch plans to be just sort of eating with them and enjoy yourself. Office hours today, as usual. There will be Math Science Skills Center hours on Tuesday, as usual. Carter will be there. That's his usual time of the week. And let's see. People have been asking about, it's been so long since we had a party in the class, a little celebration. So The third celebration, just to let you know, is on the 22nd, in case you were getting a little sad. So, we could like do a mock celebration at a review session sometime or something, but I think you'll have to wait until the 22nd for a real one. Is everyone comfortable with this? So just want to let you know. The Alex bars were dancing along for a while, and then they stopped. Like the music stopped playing or something. So I would encourage you, if you have not advanced your Alex bars, now is a good moment. Now is a good moment to advance your Alex bars. Okay? So make sure you're working on Alex. So it's important. That's kind of like your homework practice for the class, right? We don't assign a lot of extra problems from the book, so that is where you do the practicing part, which is super important. Questions about the course in general before I move on to talking about molecular orbitals. I read this morning that many of you have a lot of questions about molecular orbitals, so I'm gonna talk a little bit, and I'm gonna let you practice a lot today. So that's the plan. Okay? So let's talk first in general about molecular orbitals, and then do the CPA. So what's an orbital? It is two things. It is an energy, and it is a region of space. That holds true all the time, whether you're talking about atomic orbitals or molecular orbitals. These things are quantized energies, meaning they have discrete energy levels. How many electrons can occupy any given orbital? And that could be an atomic orbital or a molecular orbital. 2 electrons at most can occupy a single orbital. So every pair of electrons has like a unique region of space and unique energy in a molecule, right? We can define every pair of electrons in the molecule. When we were talking about valence bond theory, why is valence bond theory so useful to the chemist? Why is it the one, when I think about chemistry in my mind, I think in valence bond terms. When I look at the world, that's the way I view matter. Why is it that model is so useful? Dan said a lot of things today, so I want someone else to answer. Why is valence bond theory so useful? Why is it sort of, go ahead, Amarachi.
Because considers the various electrons that is the key parts.
Absolutely. It's dealing with those key electrons in the valence, right? And using valence bond theory and really just a pretty simple set of things. Like in a week, you were able to sort of develop the skill to know what orbitals were overlapping to form every bond in a molecule and where the electrons came from and whether it was a sigma and pi bond. In a week, you were able to sort of understand molecules, the structure of molecules at that level. As it turns out, that level of understanding, you can look at a protein that has literally hundreds or thousands or millions even of atoms, and you can understand its structure using valence bond theory. You can look at almost all of organic chemistry, and you can understand what's going on in terms of the structure and even some of the reactivity when you just know valence bond theory. It's something that just becomes really familiar really fast. However, when we say we're only thinking about the valence electrons, we've forgotten about all the other electrons, right? Not that we've forgotten about them, we know we're there, we're just not really accounting for them in our model. So as it turns out, the best description of matter takes into account what's happening for all the electrons. And the behaviors are kind of similar to what we saw in valence bond theory. We have orbitals that are coming together, and they're making new energy levels and new shapes in space for electrons to hold. And kind of things, there are a lot of familiar things from valence bond theory, like when 2 atomic orbitals come together, how many molecular orbitals are going to result? 2 orbitals together, they're going to mix to form 2 new orbitals. So every time you put an orbital in, you get an orbital out, and they're going to mix. And so what happens in the real world, and we sort of looked at some pictures last time, is all the atoms coming into a molecule, that could be thousands of atoms in some molecules, coming together, they all bring a set of atomic orbitals, and when they get together, they all mix with all the atoms. So now we're talking about tens of thousands of different energy levels, right? It gets very, very complex, right? No wonder your book starts with diatomics, right? We're looking at the molecular orbitals diatomics, because those are the ones we can sort of get a little handle on to sort of understand what's happening. So what we're doing right now is we're sort of developing a little bit of intuition about what's happening with the rest of the electrons. And if we really want to understand what's going on in a molecule at a deep level, we actually have to address all the electrons. And if we want to understand how light interacts with matter, we need to understand what's happening with all of the electrons, all of the energy levels. Is everyone comfortable with this? So this is not something you sort of do on a casual basis. You need a computer or now an iPad or even a phone, and you can compute all those energy levels, and you can compute those regions of space, but it's not something we do sort of casually, like we do with valence bond theory. Valence bond theory is something you can do at a party with your friends, right? And I'm sure many of you have already tried it, right? Like it's something that you do on the weekends or with your relatives at Thanksgiving. It is a really good thing to do at Thanksgiving to talk about the valence bond model. I feel that it brings family together. It's one thing that everyone can agree on, right, Carter? I mean, it's a special thing. So it's not quite as good as NMR spectroscopy, but we're not quite there yet. NMR spectroscopy is the thing to do with family. It is the thing. Anyway, that more on that next year. So let's talk about this. So let's draw the Lewis structure for oxygen. So I just want to let you know why we're talking about molecular orbital theory and what it's about. And we're going to deal with a few limited examples so you get a sense of what you can do with molecular orbital theory. But if you want to really deal with it, we need to compute things and look at regions of space and energies that are computed. Okay, so let's start with, what's the Lewis structure for oxygen look like? So I have two oxygens. How many bonds between them? Two. How many electron pairs on each one? Two. Okay, we're not going to go through in detail. You guys are pros now, Lewis structures. So it says, draw the molecular orbital energy level for the oxygen molecule. And so here is kind of walking you through the steps. Remember what I said? Atomic orbitals, all of them come together and they mix to generate the molecular orbitals, right? So what I've drawn over here, right, so there are kind of like three pictures here. There's an atomic orbital picture here, there's an atomic orbital picture here, and in the middle is the molecular orbital picture. So what orbital would this one be? What's the lowest energy orbital? Yeah, so we've got like 1s way down below, right? And we could draw it. You want to draw that one too? You could draw. Did you guys draw the 1 or just the 2s?
Just the 2.
All right, let's start with the 2s. So, there are 2 electrons way down there that we didn't consider in each of the atoms. So this is going to be a 2s, and this is going to be a 2s. This is on one atom, and that's on another atom. Is everyone comfortable with that? And then what are these? These are the p's. One of them's a px, one of them's a py, and one of them's a pz. People ask me a lot of questions. Which one's x? Which one's y? Which one's z? They're just relative orientations to each other, meaning they all lie on mutually orthogonal axes. So if you want to call a pi bond the overlap between two y's, that means you define those two as like a lateral overlap of those two. You know what I'm talking about? So you get to decide which one's going which direction as long as they're all orthogonal. Every x is going in the same, every y is going in the same. So we would have the same kind of thing here. We would have like a px, a py, and a pz. So these are the orbitals, and these are of course two p's. Oftentimes you leave that off. Those are the two p's. When the two s's come together, we already have a sense of what's going to happen. We're going to form a what kind of molecular orbital here? This is going to be a sigma bonding molecular orbital. Why do we call it bonding? How do we know that it's bonding? It is lower in energy than the separate atomic orbitals, right? So the two that went in to combine to make it have an energy, and if the resulting mixed orbital is lower in energy, we call it a bonding molecular orbital. What that means is if there's an electron from each of those orbitals that then goes into each of those atomic orbitals, comes in separately with an energy, if there's a molecular orbital of lower energy where they can both sit, that means the structure has become more stable. That's why bonds happen, because we put electrons in an arrangement that they're more stable than they were when they were atoms, right? So in any case, we have that. And then what's the next one going to be? Yeah, this is the corresponding antibonding orbital. This is the sigma star antibonding MO. Okay, so the star usually denotes like antibonding. And now we have sort of two different groups, it looks like. We have kind of like one that has a unique energy. What's that one going to be? This is going to be the sigma combination of the p orbitals, right? So what kind of overlap is that? Lateral or head-to-head? That's the head-to-head overlap to make a single bond between two p orbitals, right? So I'll just sketch it really quick to make sure people sort of get it. We have two p orbitals that are going to come together, right? One here, and if they're in phase, there's constructed interference in the middle, that makes a sigma bond, right? So that's this one. So this would be a sigma. We would call it like a 2p, sigma 2p bonding MO. Right? Everyone comfortable with this? Then we're going to have two different, what kind? Pi. We're going to have two different pies. We're going to have one pi where we have a lateral overlap like this between the p orbitals, and one where we have a lateral overlap like this. They're mutually orthogonal, right? So you've got a pi overlap like this and a pi overlap like that. Okay, so that's the rest of them, right? So these are going to be like pi 2pz if you want, bonding molecular orbital, and this is going to be a pi 2py bonding molecular orbital. And I don't care whether you use x's or y's or z's as long as you're consistent, right? So these are the bonding combinations because they're more stable than the p orbitals that came in. Does everyone see that? There's going to be a corresponding set. We took 6 orbitals in. We need 6 orbitals out. The other 3 that are going to come out are going to be the higher energy ones, right? Those are going to be the higher energy ones. So these two are going to be the 2pz star, pi 2pz star, antibonding orbital. The star means antibonding. And then this is going to be the pi 2py, just because of the way I chose the letters. And it's going to be a star. Just chose the letters that way. Everyone comfortable with this? And then what's that last orbital at the top? Yeah, it's going to be the anti-bonding sigma orbital. So that's going to be the sigma star 2p, right? And it's going to be like, I guess x is the one they combined to make it, right? So we call it the 2px, anti-bonding molecular orbital. Is everyone comfortable with this? So basically, what this is describing, again, this is like the simplest possible molecule. We're only talking about 2 atoms coming in. If you had 5 atoms, all of the orbitals would have come together and mixed to make a more complicated picture. Is everyone with me? It's hard to talk about more than 2 at a time. If you want to talk about more than 2 at a time, what do? You get your phone out and you load WebMO and you draw the structure of the molecule, and it will literally spit out the energy levels in the regions of space. That's the tool. Go ahead, James.
In the textbook, it had like going from lowest energy to highest energy. It started with the pi 2p bond.
It depends on which element it is. We're going to deal with that today in the challenge. Okay? It depends on which element it is. As it turns out, the energy spacing switches when you go from nitrogen to oxygen. The energy spacing switches. This is the reason why I don't want you to memorize that. I want you to be able to use Aufbau principle now to fill up electron density. That's why we use computers to define those energy levels, because it's not something you can intuit, right? The energy levels are going to change relative to one another depending on the nucleus and the electronegativity and all sorts of things. Okay? Good question. Great question. So how many electrons are going to be in sort of the 2 subshell or the 2 shells? How many? For oxygen, right? We're dealing with oxygen. Looks like in the 2s we have 2 electrons, and then in the 2p we have 4. Right? Is everyone with me? So each oxygen is going to bring in an atomic orbital, a 2s orbital that has 2 electrons in it. And then how many here? And up in the 1, 2. Where's the next one going to go? Yeah. It doesn't matter which one, as long as I'm just, Is everyone comfortable with that? So that's what's coming in on the atomic side. All of those electrons now have to find their way into molecular orbitals. And we're going to do an Aufbau principle. We're going to start at the lowest energy and just build up. Aufbau means build up. So we're going to start pouring these electrons in. So I've got 2 electrons. This takes care of half the electrons coming in on the S's. And then I've got 2 more. So now I've taken care of these 4. Everyone comfortable with that? And then I've got, let's see, a total of 8, it looks like here, so I'm going to do, I've left myself no space. 1, 2, 3, 4, 5, 6, 7, 8. Does everyone see what I'm talking about? So I just filled those in. You're going to have lots of chances to do this in just a minute. So this middle thing is the molecular orbital picture of what's going on. And we can write a molecular configuration for this molecule. These are the names of the orbitals rather than like 2s2. Now we're going to have like sigma 2s. And how many are in the sigma bonding 2s? 2. And then we're going to have the sigma star 2s. How many electrons in it? It's just like a molecular, it's just like an atomic configuration here. We're doing a configuration. So what's the next one going to be? Sigma 2p. And is it star or not star? Not star. How many electrons are in it? 2. And then we're going to have the pi 2p's. Those are the orbitals that came together. How many total could we fit in there? 4. We've got 4 in there. Everyone comfortable with how I'm doing this? And then what's the next one? Let's finish the configuration. Then it's going to be pi 2p. How many are 2p star? 2 electrons total. Okay, is everyone comfortable with that? That's a molecular electron configuration. It's just like doing an atomic configuration. Amarachi wants to go.
Not necessarily need to do this in textbook because, like, in the textbook they have pi 2p1 to another pi 2p1 to.
They just separate them out. Yeah, you could do the px and the py separately. So you can break these up. What Amarachi is suggesting is you could break this up into the I chose z and y. Does everyone see that? You could show whether that's occupied or not. The reason why I didn't is those are what we call degenerate. Remember what degenerate means in MO theory? Equal in energy. Yeah, equal in energy. So because they're equal in energy, I group them together. Okay, I'm okay either way, but it's a good point. Okay, so there we go. Let's see. Draw a picture of the pi 2py bond between the two atoms. Use dotted line to show any nodes. So what's the pi 2py going to look like? Is it a bonding or an anti-bonding orbital? Bonding. So we're going to see a buildup of electron density between the atoms. So is it going to be like the lateral overlap or the head-to-head? The lateral overlap, right? So we're going to see a picture that looks like this, and Dr. Mock loves the dotted one for the nodes. So like, actually there's like a node there in the plane, and then there's like a node between there and there. So I guess you could get away with just the node between on this one. And this is one phase, and that's another phase. So we've got that node there in the middle. Is everyone comfortable with this? Mm-hmm. Yeah? Okay, now a lot of people ask this question about, this G shouldn't be there, sorry. Is oxygen in its elemental state paramagnetic or diamagnetic? How do we tell? Paramagnetic, you look at what to figure out paramagnetic? If there are unpaired electrons in the molecular orbitals, are there any that aren't paired? Yeah. So what does that mean? Paramagnetic, right? That means it interacts with the magnetic field. That's what that means. Okay? If they were all paired up, it would be called diamagnetic. Boom. Let's do the challenge. You get a lot of practice doing it in the challenge. I'll address your question, but let's get started on the challenge.